All right, let's just jump right in. For the longest time, string theory was hiding a pretty big secret. We had a really good handle on how strings behave when their interactions are weak, when they're just barely tapping each other. But what happens when you really crank up the dial? When those interactions get super strong? For decades, that was a total black box, a blank page in our understanding of the universe. Well, today, we're going to fill in that page. I mean, it's a question that probably keeps a few physicists up at night. What if the very tools you're using to look at the cosmos have a giant blind spot? What if there's a whole layer of reality that's just invisible to your math? For string theory, this wasn't some late-night philosophical question. Nope, it was a very real, very big problem. You see, the main mathematical tool that physicists were using is something called perturbation theory. And it works great when you treat interactions as these tiny, polite little corrections. It's fantastic when the coupling constant, which is just a number that tells you how strong the interaction is really, really small. But as that number gets bigger, the math doesn't just get difficult. It completely throws its hands up and breaks down, spitting out pure nonsense. The theory was essentially blind to the entire world of strong forces. So, for a long time, it really felt like physicists had this amazing book that described all of reality, but one of the most important chapters, the one on strong coupling, was written in a language that absolutely no one could decipher. Let's really break down why this was such a huge roadblock. Perturbation theory is built on the assumption that interactions are just little afterthoughts. But in the real universe, some of the most fundamental forces, like the stuff that holds the nucleus of an atom together, are incredibly strong. So by not being able to handle a large coupling constant, string theory couldn't claim to be a complete picture. It was this incredible theory of everything that was missing all the really intense parts. So how did they finally figure out how to read that impossible page? Well, they didn't just find a better magnifying glass. They found what you could only describe as a kind of magic mirror, a concept that would completely change the game for physics: duality. So what is duality? It's a really profound idea. Picture this. You've got two different physics theories. They look totally different on paper, different particles, different forces, completely different math. And yet, they make the exact same predictions for any experiment you could possibly run. They're physically identical. It's kind of like looking at a statue. From the front, you see one thing. From the side, you see something totally different. But is it a different statue? Of course not. It's the same object. Duality is that same idea, but for the laws of the universe itself. Okay, let's look at a real-world example to see how this works. We'll take one of the string theories, called type 2 IB. Now, when its coupling constant G is small, so weak interactions, the main players are the fundamental strings. They're light, they're simple, but there are these other things called D strings that are super, super heavy and kind of stay in the background. Now let's crank G way up, making the interaction strong. Suddenly the fundamental strings get incredibly heavy and complicated, but here's the magic. The D strings become super light. The physics of this messy, strong theory with a coupling of G is perfectly, and I mean perfectly, described by a simple, weak theory with a coupling of 1 over G. They're dual to each other. And that is the absolute key. That unreadable page of strong interactions, it wasn't a harder problem, it was the easy problem just viewed through this duality mirror. All of a sudden, physicists had a backdoor into the strong coupling world. All they had to do was study a different, much simpler, weakly coupled theory. It was an absolute revelation. But this duality mirror didn't just give them a new perspective on things they already knew about. It started reflecting something else, something brand new. Something that no one had ever predicted was hiding inside string theory all along. Naturally, this led to a very tantalizing question. Okay, if this trick works, what happens if we take another one of the string theories, type IIA, and just crank that interaction knob all the way up? What do we find when we push that coupling constant to its absolute limit? The answer was unexpected, to say the least. It turns out, as the coupling constant G in that type 2A theory gets bigger and bigger, something else just appears out of nowhere and starts to grow with it. A new 11th dimension of space. It was there the whole time, but it was curled up into a circle so incredibly tiny that our weak coupling tools could never ever see it. The strong coupling was like a key, unlocking this hidden dimension and letting it expand. For decades, everyone just knew. The magic number for superstring theory was 10 dimensions. That was the rule. But this discovery just blew that wide open. The universe, in this deeper picture, didn't have 10 dimensions. It had 11. And this brand new 11-dimensional framework that stepped out from the shadows of strong coupling, well, it needed a name, so physicists started calling it M-theory. M-theory became this grand parent theory The single source from which all the 10-dimensional string theories we already knew about seemed to emerge. And you have to love this little detail. The M was left deliberately vague. Did it stand for mystery? Or maybe magic? Or, as physicists would later realize was more appropriate, was it for membrane, these higher-dimensional relatives of strings that are the real stars of the show in this theory? It just perfectly captures that sense of wonder and discovery. So what did finding this 11-dimensional parent actually do for physics? It provided the single, elegant, unified picture that everyone had secretly been hoping for all along. You know that old parable of the blind men and the elephant? It's the absolute best way to think about this. For years, string theorists had these 5 completely separate but equally valid theories. And it was kind of weird. Why 5? Well, M theory is the elephant, the one single true reality in 11 dimensions. The 5 string theories, they were what the blind men were feeling. One touched the tusk and shouted, "It's a spear!" That's like, say, type I theory. Another one felt the leg and said, "It's a tree." That's type 2I. They all thought they were describing totally different things, when in reality, they were all just touching a different part of the same elephant. So in the end, duality wasn't just some neat mathematical trick. It was the Rosetta Stone. It was the map that connected all 5 of these different theories, linking them all together and showing that they all came from the same common ancestor, 11-dimensional M theory. It was the grand unification they'd been looking for. And why does any of this really matter? Because M theory and duality finally gave us the tools to attack those really hard, non-perturbative problems. It gave us one single cohesive story. It introduced us to totally new objects in the universe called brains. And maybe most importantly, it opened the door for physicists to use string theory to calculate the precise properties of black holes, a massive step towards a real quantum theory of gravity. The journey into strong coupling really showed us that our view of reality was just incomplete. A whole dimension of space was hiding in plain sight, right there in the math, just waiting for us to find the right way to look at it. It proved the universe is way more interconnected and mysterious than we ever gave it credit for. And it leaves you with this amazing thought. If something that huge can be hiding from us, what other incredible secrets is the universe just waiting to reveal?